So now that we've run .fit and pointed to our inputs in S3, that's going to go provision the instances, run the training job, and give us the results back. Let's go to our cooking show version. Again, you can see multiple instances reporting lots of different logs. Sometimes our logs are a little bit verbose, but the main information that we want is going to be down here in the evaluation section. So if we look at the evaluation, we can see that our model gets 98% accuracy, which is already really good. MNIST is not the most challenging computer vision problem, but still 98% accuracy is actually pretty good. And our loss is 0.05, right? So we'll try and now take this and tune the hyperparameter values and see if we can get a better loss. So improve upon a model that's already doing pretty well at MNIST, right? So how we do that is we create an estimator again, and this time everything's the same as last time. I'm calling it tune estimator. Everything's the same except I don't specify any hyperparameters here, right? So that tells my model, hey, I'm going to tune these hyperparameters, right, by not specifying a static value. You can specify some static values if you don't want to tune them, but we're trying to tune them. So now I'm going to specify my hyperparameters separately, and I'm going to use some of the pre-built functionality that, again, we have in the SageMaker Python SDK. So we have these constructor classes, continuous parameter, integer parameter, and categorical parameter, right? And continuous parameter is anything that takes a value in between, a real numbered value between the min and the max that you specify, min and max, right? Integer parameter takes an integer value between your min and max, and then categorical takes one of a finite set of values, right? So I said we'd learn a little bit more about these hyperparameters later. So we've got a couple of cool links here. Part of this is just me sharing links that I like. So you can see here, this is a kind of a nice little website that shows you how changing learning rates can change your convergence of a variety of different functions. There's one that I like. That one. Okay, so you can see if I change learning rate. Oh, I'm still on a different algorithm, aren't I? Oh, I'm in Neldermead. I need to be on SGD. Gradient descent. There we go. So gradient descent, you can see how this works. This is, imagine this being hyperparameter value 1, hyperparameter value 2, and then the hotspots being areas of low loss, right? So you can see how changing that learning rate and drastically decreasing it, I take much, much, much slower steps. Drastically increasing it, I take much bigger steps, but I also risk missing, right? And so you can see it's really important to finely tune these values. We actually got really good performance on MNIST with the kind of naive guesses that I tossed in there, but it can be a lot more challenging than that in different problem settings. And so we want to be cautious about tuning them. And so that's where SageMaker automatic model tuning comes in. We can tune learning rate to find our network weights a little bit easier. Sorry? Well, sure, yeah. So let's see. Okay, so that if you wanted to change between like SGD and Atom, you would do that in your TensorFlow script, right? So here we've hard-coded, where have we done it? Right here. We've hard-coded using the Atom optimizer, right? And so Atom has a certain subset of hyperparameters that are always going to get used. Some of the hyperparameters I have are, like learning rate, are going to be for Atom. Some of the hyperparameters I have are going to be convolutional filter size. That's actually about the network architecture itself. If I wanted to do an if statement here, I could bring in my hyperparameter and use SGD versus Atom, right? I could do those two things with just an if statement, right? I mean, the same way I have an if statement up here to use either TF sigmoid or TF ReLU, I could just use either Atom or SGD or something like that. Right? Okay. Good. So I specify those. Activation functions, we probably don't have to talk too much about, other than, I already kind of mentioned, that's the nonlinear step that you add into your neural networks. So you can go check out this site if you want and look at what the difference between a ReLU is, where essentially you just, anything less than 0, you set to 0, and a sigmoid, which is kind of the more old-fashioned activation function in neural networks. That looks like the S-curve, right? So we've got our hyperparameter ranges, we've got our hyperparameters defined, our ranges and our distinct values. And then we just want to talk about what our actual metric is going to be. In this case, we're going to try and minimize our loss. And we just set up a regex. And that regex is going to scrape through our logs and pull out the value that matters, right? Loss equals, and then any number, it's going to grab that. And it'll return the last value, so whatever you report last, which in our case is the number we showed, which is that evaluation loss, right? Is this figure right there. It's going to just pull that line out in the regex and grab that 0.053 number, right? So we now create a hyperparameter tuner. This, again, another constructor from the handy SageMaker Python SDK. We pass in our estimator, our objective metric name, our hyperparameter ranges, how many jobs we want to run. So you can run, 5 jobs, 100 jobs. Depends on how big you want to search and how big your search space is and how many hyperparameters you're trying to tune. You can set up different number of max parallel jobs. As I mentioned, SageMaker builds a meta model to try and predict where good hyperparameter values will be. And so setting that really high gets you done faster, but maybe less accurately. So we'll set that low. And then we just dot fit and, again, pass in our S3 path, right? So that tuner is going to orchestrate kicking off 20 other training jobs at a time, learning about hyperparameter values and what kind of model fits they produce, and then kicking off more training jobs with better and better hyperparameter values in order to try and really optimize the model. Right? Good.
So let's say you have 2 different hyperparameter variables, and each of them have 3 items. So in total, you are doing 9 experiments to find the optimal parameter. And if your data set is huge, and overall it takes about 8 experiments, you're essentially doing 9 days of 9 different machines in a day. So is there a way to use a subset of data randomly for hyperparameter tuning, or do you have to use full data?
You could certainly, pre-sample it down in S3. You could do something within your TensorFlow code to just bring in a certain portion of the data. The best option is probably doing it in S3, either creating special manifest files or however you may want to make that work. We've passed in an S3 path, but you can also specify a manifest file, so just pick and choose just a couple of files if you had lots of them. The interesting thing is, if you do all categorical variables, you're essentially doing grid or random search at that point in time. And you can run them all in parallel if you want, right? Really, the continuous and integer variables and the mix of those things with a categorical variable is where the model is going to learn something and try and do something better, right? It's gradient-free optimization, but it still requires some degree of flexibility, right? So it's deliberately not a grid search method because grid search can be so exhausting to try and test all those values, right? So we do a dot fit here and point it to our S3 data. That's going to run for a long time. Let me actually kick one of those off. Logs. Okay, better. All right. Okay, so I've kicked that off, and let's go and track it now here. So I can look at my hyperparameter tuning jobs, and you can see that I've got it in progress, right? And this is going to allow me to kind of keep track of how that's kind of going as I'm doing it. So if I kick off 100 jobs, I can kind of monitor as I go and stop early if I need to. But here's a completed one. So here's one where I ran all 20 jobs already. And you can see I've got some data here. But that's no fun. Let's bring that data into a Jupyter Notebook and analyze it, because that's more fun. Whoops. So we've got another constructor here, helpful constructor, tuning job analytics. We're going to pass in our current job name, and we'll just get a data frame of that same data, right? So you can see all of the objective values across the 20 different jobs that I ran, and how much time each one took, what the hyperparameter values for them were. So the best job is 0.038, so something like a 30% improvement in loss on a job that was already doing a pretty good job. And I did that by having a convolutional kernel size of 4, a ReLU, using activation function of ReLU, and a learning rate of 0.004698, right? So we can take that job and we could deploy it if we wanted to. Like I said, we won't go into the deployment aspect of it. We'll just, kind of do a little bit more analysis to try and understand that space. Uh-oh. My Jupyter lab doesn't like my JavaScript bokeh. Let's go back here and look at it. Oh. All right. Didn't like that either. Let's... I think it's because I saved these to S3 and then returned. Let me see if I can try and get the bokeh plots to load up. They're actually quite nice looking. Sorry, bear with me for a second. Let's open that up. So we've got a little bit of code here in this to look at like that. Okay. Is it working on anybody else's screen? Probably not. I think I broke it forever by saving it to S3. There we go. All right. Ah, there we go. Okay, finally. So make sure everybody can see that. So we've created some kind of cool little plots here to show that over time, as we run more jobs, we get lower and lower losses, right? So you can see here, we start with a loss that's very high, and then as we run more and more training jobs, we get better and better. But we still do some exploration, right? So it's not like a straight monotonically decreasing function where we're always getting better. We're always kind of trying to balance that explore-exploit trade-off, where we're exploring a little bit of the hyperparameter space, but when we find good values, we try and focus on them, and then run more jobs very near in on that space. And so that gives you a very powerful mechanism for tuning hyperparameters. And then you can also look and say, which hyperparameters meant the most. You can see these learning rates were really pretty awful. These ones did okay, although they're all kind of universally awful. They're also kind of universally decent, but let me... I both love and hate bokeh. Go, move. should be able to pinch this and zoom in. But you can see that, as I change my learning rate, I get sort of different model fits, and different kernel sizes will result in different model fits. 4 does well sometimes, but also terribly sometimes. And that different types of activation functions, sigmoid is obviously inferior to ReLU, right? So I can learn a little bit about my hyperparameter space, use that to inform a future job run, and do that kind of work. Cool. So, just kind of thinking back about it, TensorFlow is designed to be an easy experience for distributing and running large arbitrary TensorFlow scripts. The automatic model tuning is designed to be a really flexible layer to wrap around things and provide you optimized model fits, right? Any other questions? It does. It works for built-in SageMaker algorithms. It works for all the deep learning frameworks, so TensorFlow, PyTorch, MXNet, Chainer, and it works for bring your own. So you can bring your own, and as long as you log your own output to CloudWatch, and as long as you take in a list of hyperparameters, it can optimize those hyperparameters. We have some examples on the GitHub repository that show how to do it with like an R algorithm, stuff like that. Very flexible. I can't tell if that's because I saved it to S3 or if I don't have it run all the way through now, so it errored up. Did it? Okay. Yeah, so right now, Jupyter Lab is in beta. It's still a beta product. I'll have to go back and figure out if that happens in Jupyter Lab if you're running it on your laptop, or if that's actually something that Jupyter Lab is looking to add functionality for in the future. So it is. Okay, thanks. Okay, so got about an hour left. I'll let people, it seems like people are taking breaks as they need them, so I'll just keep charging through and go on to another example here. And we can kind of wrap this up and hopefully, still have about a half hour for you guys to come up and ask me any questions or play around on your own and see how things work. Okay? Minimize that down. So I mentioned FastAI at the beginning. It's a massively open online course. And it's a lot of people are using it to kind of get up to speed with deep learning, which is not always the easiest thing to get introduced to. Jeremy Howard tries to make it very easy to get kind of best-in-class, state-of-the-art accuracies without a lot of necessarily investment on your behalf. And it comes with a FastAI library. And so a lot of people like this FastAI library because all the kind of best practices and heuristics that he uses and that he thinks about are kind of baked into this library. But this library is just sitting on top of PyTorch. It's using PyTorch under the hood to do all the deep learning framework stuff. And we have a pre-built PyTorch container. So I thought it would be good to kind of show the contrast between how easy it would be to go take a script that you found online. In this case, we're going to use lesson 3 of the FastAI MOOC, which is about doing structured data prediction, and take that code and run it in SageMaker, right? And so it's a big, long notebook, and it's got a bunch of messy pieces to it, and it's using pandas and converting CSVs and all kinds of things like that. Really what we've done is create our own FastAI container based on the open source SageMaker PyTorch container, and then taken that and used it to train this lesson 3 model from FastAI, right? So it kind of provides a lot of flexibility in the interface. It tries to show off what bring your own container might be all about, as well as kind of showing you how to use kind of a cutting edge package to work on your deep learning workloads, right? We have this lesson 3 Rossmann. I've made a couple of modifications to this, but this is essentially the exact version that's available on GitHub. I do a conda install up here to install some of the packages that aren't currently there. FastAI isn't a part of SageMaker right now. So you just have to pip install it. And after that, from there on out, it's pretty much exactly word for word this script. And I'll walk through this one relatively quickly because, like I said, there's lots of different components, and I advise you to watch the Massively Open online course at your kind of leisure. It's great to kind of walk through it in more detail, but the main goal here is to fit a structured prediction model that comes near the top 3 performance of a Kaggle competition, right? And so to do that, he builds this model that takes tabular data in. All the continuous variables are just kind of in a feed-forward neural network, and then he uses embeddings for all the categorical variables. And again, sort of like word embeddings that we notice that you can get all these rich relationships between how words interact. You can do a lot with embeddings just with any sort of categorical variable that you may have in your data set. And so it's very, very common to have a lot of tabular data, but have that data be a little bit messy. And so that's why this is, I think, kind of a good representative example of what a lot of people would see, is because this is based on a Kaggle competition of a Rossmann, which is a German supermarket chain, and it's using their real data, right? So I get those files from FastAI. We don't actually even run concat CSVs, but we have a variety of tables here. So we have training data and data on each of the stores, data on Google Trends, weather as well, and then a test data set. So we'll read each of those into a CSV and take a look at each of those. You can see our store data is each store, each day, how many sales they had, whether they were open that day, whether they had a promotion going on, did they have a holiday, state holiday or school holiday during that day. Store information, so what kind of store type it is, what kind of assortment it has, where the nearest competitors are, how far apart they are, how long they've been open. Different information about the states that's needed just as a mapping, so that you can add the Google Trend data to that data set and the weather data. So we've got mean temperature, dew point, max humidity, a whole bunch of different weather attributes here. And then just a little more holiday information here. So this is a little more information about stores and, this is the test data set. It's actually just like the training data set, except it doesn't have sales on it, right? So this is actually store day, right? And so he does a lot of feature engineering and cleaning here. He brings in the data sets. He does things like binarize features. He starts joining tables on to one another. He grabs some of this trend data and he munges some of the strings so that they can be joined together. He's adding date parts, right? So he takes a date and he splits it up into the year, week, month, time, day of week, things like that. Gets the Google Trends, splits it out so that there's an overall trend and a store level trend, or a state level trend, I should say. Joins the data frames together. Again, lots of pre-processing here. That's kind of very standard. Fills in missing values for some of the things that he needs. Does a couple other missing value imputations. Gets rid of some outlying data. Converts some competition data around. A little bit more. Now he's doing some rolling things, some things to look at how long it's been since a holiday, how long it's been since the competitor was last opened. So he does some rolling information. Again, just a lot of the typical pre-processing that you'd see with tabular data that a data scientist would do in pandas and maybe not like to always replicate once they've gotten it working once. And so you've got all this, and you come to the end and get a data set that looks something like this. Each date, each store, a bunch of holiday information. That's not the final data set, but it's close to it. That's the final holidays anyway. He outputs the data, creates a couple of more features here, and then he gets to his final data set, right? And now his final data set has a bunch of categorical variables, things like store, day of week, year, month, day, state, holiday, whether how many months the competition was open, and then continuous variables. So things like how far the competition is away, temperature, other weather information, Google Trend information, and promotions and things like that that might affect sales, right? And he joins that all together. At one point in time, he kind of does both things where he samples and then uses the full data set. We won't worry about that too much. Creates a validation data set, which he's already keeping in information from the future there, so I won't get too deep into that. And then generates this metric, exponential root mean squared percent error, which is what the Kaggle competition was actually based on, right? So he now creates this columnar model data set, right? And he passes in the path to the data and his data sets, so his data frame that he's using. And now he's going to create these embeddings or specify these embeddings. So he's getting a count for how many distinct values of store he has. He has 1,116 stores. He has 8 different days of the week, 7 days of the week, plus an unknown category. Apparently some of the data is missing, so he's had to create an unknown. And then he decides to use a heuristic for how big his embedding space should be. So when we did those words, we had a big corpus of text, and we reduced it down to 100 dimensions. In his case, every continuous variable gets its own unique set of embeddings, and he makes that dimension half of the distinct count, or max 50, right? So none of the embeddings are bigger than 50 dimensions, but most of them are just half of this relatively small number. So that's a heuristic. Again, we could tune that. And then he calls getLearner, and this is what actually builds our model. This is what's actually building the neural network behind the scenes. He's using see if that, oh, that's going to error horribly. Anyways, getLearner, we'd have to go to the help setting to figure out exactly what's going on there. Let me see if I have a pre-run version of this real quick. Here we go. So, oh, his help function doesn't say anything. Whoops, he didn't document this very well. Sorry, this parameter is for dropout. This is for how many layers I think he's going to use and different learning rates, I think, at each layer. He creates a neural network out of that and then does this learning rate find functionality to try and find the right learning rate. Again, a lot of heuristics and things that he's used to, a lot of the interactive sort of work that you would see a data scientist doing. And the purpose of it isn't to kind of talk through all of these steps. That's a little less important than how do we get this in SageMaker, right? So we've got this big pandas, kind of dog's breakfast of a lot of different manipulations. We've got these different jobs that we're running, and at the end we kind of save a model out here. And that's what we really want, because that's what we want to put into production, right? We want to take that model that we've trained and put that into production. We could either run this in the notebook and then just put it into production with SageMaker, or if we wanted to train every week, we wanted to train the model with new store data, we could do that by using kind of SageMaker training and using this sort of setup. So what I've done here is created a few things, right? So this is a notebook that walks through what it would look like to productionalize that in SageMaker, right? So I basically took this, and we talked about being able to export as a .py file. I exported it as a .py file, and I made a few minor modifications, right? So I start by setting up the same things that I always would in SageMaker, and then I'm going to go to that file. It's not. It's in the .tar.gz that you downloaded. So I've created this train.py file, right? And this train.py file is, like I said, exactly what it's this lesson 3 Rossmann IPyNB converted to a .py file, and then I've just made a few minor modifications. The real minor modification I've made, instead of setting the path as a hard-coded string, I use an environment variable that comes in on our containers, and this is documented, right? I delete a few steps that do prints and things like that just because I don't want them. And then at the end, I've added this torch.save, right? So I save the m.model out to the model directory, which is again an environment variable, and I call it model.pt, right? And so that's really the main changes I've made. I've taken this giant script, dumped it out as a .py file, lopped off the top so that I have a little bit more flexibility, and then at the bottom wrote my model out to a permanent directory so that when I train it in SageMaker, it'll be back output to S3, and I'll be able to use it, right? So I know what my training is going to look like. Now I want to kind of know what my hosting is going to look like, right? So my training is basically a rote copy from the Fast AI course, right? So I found a script on GitHub. I want to run it. I was able to do that very easily. Now I want to do some predictions off of it. So I want to do the code I need for a real-time endpoint. So in this case, I want to train in a GPU and host in a CPU. So I create this model function, and this loads my model, right? So this is my serving or my hosted endpoint loading my model, right? So model.pt, same file I stored. And it uses this little magic thing to load it as a CPU model. But that's it. It's just torch.load. I take an input function, right? So I know that I'm going to pass in a JSON body to get a prediction. So I just have to turn these into torch variables because that's what the model is expecting. So a long tensor wrapped in a variable of the JSON input that I provide of categorical variables go to a long tensor, and then the continuous variables go to a float tensor. And then my predict function is just me calling the model, just like I would with PyTorch, passing in that input data that comes from this input function. And then my output function, I just dump my prediction back out as JSON, right? So really simple here, 20 lines of Python to have a real-time prediction generated from this model that I trained, right? Yep. That all came along for the ride. That was, like I said, I literally took the IPython notebook and I changed the top here, this path variable. Everything else, all the pandas came along for the ride, right? Whoops, sorry about that. All of the joins, all of the adding the date parts, all of the, whoops, I keep doing that. All of the imputation of missing values, all of that. Didn't have to change any of it. During the prediction, you could set that up in, I actually grab a row from, whoops, get to, got my zoom up too high. All right. So down here at the bottom, I actually just grab a record from my data set, and that's what I pass in. I assume it's either pre-processed coming into the endpoint, or if I wanted to, I could include it in my input function. So instead of doing a JSON load, I would load something else. I would load in CSV strings or something like that, and then I would include all the preprocessing logic in there. Right? So now that I've got that set up, I want to change the container. Right? So I mentioned we have this pre-built PyTorch container. If you want to bring your own container, it's actually quite easy to base it on what we've built. Right? So I mentioned those are open source, and so I've downloaded those here. It's actually sitting in that .tar.gz, SageMaker-PyTorch-container. Right? So that's the GitHub repository that we have for a PyTorch container. They have their own Docker file. I modified that. The main modifications I did, Python 3.6. We still use 3.5 because it's Ubuntu 16.04, and that's what's in Ubuntu 16.04's repository. However, FastAI uses 3.6, so I had to go to get a repository outside of that. So I get Python 3.6, and I pip install FastAI. Right? I just changed the Docker file by 2 lines in order to get my own version of the SageMaker PyTorch container that now runs FastAI scripts. Right? And then I grab the build logic from the GitHub README. Right? So I just have some build commands here that I call, and that's it. Right? The rest of this is just making sure it works with whatever region you specify and whatever algorithm name you want to specify. Right? But I'm going to go build the Docker container. One of the nice things, Docker is already deployed locally in the notebook instance, so you can build Docker containers there. That's what I'm actually relying on here. And then I upload my files to S3. We already talked about the training file and how I didn't change anything. We talked about the hosting file. Whoops, I skipped something. Skip the estimator, right? So now I've got my own Docker container. This is the string for that, right? So I've just called it PyTorch. I probably should have called it FastAI, but that's the container I've built. And I pass that in as the image. I pass my train.py in to train, and I do .fit, and I pass in an S3 path, right? Again, specifying my same hardware. I can be running a T2 locally, but I can have a P3 2x large running in running the training of this actual job, right? So I can take advantage of a GPU just for the fraction of time that I need it, rather than using it to orchestrate and run all of my code, right? So that produces this output, sends it to the output. You can see we're getting pretty good fits. So we've got like a 0.03. If we go back to, so if we go back, if we had fit a random forest on the same data set, which is another popular prediction algorithm, 0.08, right? So, far less than half of the inaccuracy. So the neural network model does a really good job. Like I said, the result there was, I think, top 3 in a Kaggle contest. And so very quickly grabbed that script, ran it here, 589 billable seconds, right, rather than an entire day's worth of time on a GPU instance. And then now I can deploy, and I can deploy to a CPU instance instead, so that I can make real-time predictions, right? So here's that record that I printed out at the end of the last notebook. I pass it in as my categorical variables, my continuous variables, and I get back out a prediction. So that's the log of my sales, right? And then I just remember to delete my endpoints. So that's the general flow, right? It's that easy to very quickly, create your own container, set up your own job to take advantage of some of the things that we've built, and grab a script off something like FastAI to do your deep learning. Cool. All right. Questions? You could set up validation if you wanted to. You know, if you, in that input function, if I got something that I wasn't expecting, instead of returning a prediction, I could return a string that says, I could return a JSON blob that has a bunch of detailed error information about how that's wrong. Hey, it's not, you don't have enough categorical variables in here, things like that. You would do your own kind of standard Python try except sort of way to send back errors that way. Oh, text plain. Yeah, so with the built-in algorithms, because you can't actually write scripts, you have to, you know, be very clear when you want to handle the very specifically supported different data types, right? So some of our algorithms accept CSV, some expect a text file, some expect you know, a Parquet file or JSON lines or things like that, and those are documented as to what they accept. For bring your own, I guess I did. I conformed to what the kind of standard is. I set my serializer and deserializer to none. You could, in that predict function, pass in a NumPy array and have it serialized to JSON for you so that you don't have to think about serializing it as JSON every time. So you have some flexibility there. But whatever code you're writing in that host.py file, you know, if it throws an error and you don't know because you got an unknown input, it's up to you to kind of log and track that to say that. And you can specify certain content types and get certain content types back, right? So these arguments will provide request content type and output content type. So those things come into you, so you know what somebody requested or didn't request, and you can validate against that, right? We don't naturally do it because it's really up to your algorithm, right? Some algorithms can accept lots of different formats, right? Right? It's really up to you. You know, you could make it accept lots of different formats too, right? You could have a bunch of conditional logic to say, hey, if it comes in as JSON, then do this to it. If it comes in as a CSV string, do this to it. Which is, you know, kind of how our algorithms work in a large sense. Is a lot of them handle two different content types. One that's a little more highly optimized, and one that's a little easier to use. And so, you know, you can have that kind of conditional logic to do multiple things. All right, cool. So I wanted to leave a little bit of time at the end, about a half hour here, so that people could kind of play around and still ask me questions if they wanted to. So if you've got your own SageMaker project that you're interested in trying out and you'd like to be able to ask me a question, I'm going to be around for a while if it's been a long day and you guys are ready to hit the pub, go for that too, right? It's your call at this point. So I'll be around though. Thank you guys all for coming. We appreciate it. Feel free to stop by the AWS booth and see how things are going. Great. Thanks, guys.